Hello, my name is Paulo Bala and I'm presenting Staying on Track, a comparative study on the use of optical flow in 360 video to mitigate visually induced motion sickness. I'll start off with some key concepts. VIMS, or visually induced motion sickness, is sometimes referred as VR sickness or cyber sickness and occurs strictly from visual stimulation. The Similarity Sickness Questionnaire (SSQ) is used to assess and differentiate VIMS, whose main symptom category is disorientation, from motion sickness and non-virtual simulator sickness. VIMS is polysymptomatic, meaning that there is multiple symptoms, and polygenic, meaning that those symptoms manifest differently across individuals. Furthermore, certain subpopulations are more susceptible. Previous work offers multiple solutions to prevent VIMS, such as non-natural travel interfaces like teleportation, walking-based techniques like walking in place and redirected walking, and visual optimizations. We are particularly interested in the latter since they are applicable to 360 video and will expand on two of such techniques. The first is independent visual background, IVB, where visual elements consistent with the real world serve as anchors when introduced into the virtual world. In previous works, IVBs used were grids, horizons, fake noses, clouds, among others. The second is field of view manipulation. Previous work proved that wider fields of view cause more symptoms since users are more exposed to the visual periphery, an area that is more sensitive to motion. A solution to this has been the inclusion of vignettes to block this area, restricting the field of view, as done by Fernandez and Feiner, where the movement speed of the player was matched to the radius of the field of view. Motivated by this last work and applying it to 360 video, we wanted to explore the use of optical flow, a motion pattern caused by the relative motion of objects in the visual scene compared to the camera or the observer. And we asked two high-level questions. How can we use the optical flow of 360 video to mitigate VIMS, and how can we apply and combine techniques that mitigate VIMS in VR to 360 video? Our goal by merging optical flow and VIMS prevention techniques is to have a technique that is only present when is needed, maintaining immersion in the medium. To answer these questions, we started by choosing a popular 360 video of a roller coaster with considerable motion. The video chosen is present on two datasets of saliency maps, and using satellite images and the original video, we segmented the track contour according to the track features like a launch track, a double dip, helices, and head choppers. We processed the video with a Gunnar-Farnbach algorithm, a dense optical flow algorithm, and exported X and Y optical flow vectors to a CSV file. To reduce file size and make it operable for runtime use, we grouped optical flow vectors every 5 frames and in 5 by 5 pixel squares. We mapped optical flow to time and used it to complete the table with a description of optical flow patterns in peaks. Based on the track description, we isolate two segments of interest, S2 in blue, where the wagons are starting to gain speed, and S3 in yellow, when the wagons are at max speed, causing drastic changes in the optical flow. During runtime, the optical flow values of the area where the user is looking at are aggregated in a magnitude vector. This magnitude vector is used to determine the size of the field of view. A high optical flow, meaning movement, requires a small field of view to limit the visual periphery. A low optical flow, meaning that the environment is stable, allows for a larger field of view. The independent visual background and restricted field of view techniques were based on the tunneling demo from the Google Daydream elements and implemented in Unity. Here you can see a simulation of the behavior in the Unity editor. A Gear VR with Samsung S6 was used for the study. Based on this implementation, we organized the user study. The study used a factorial design with two independent variables, IVB and restricted field of view, resulting in 4 conditions as you can see on the right side. 24 participants experienced the 4 conditions in a random order over a period of 2 weeks with at least a day between sessions. Prior to the study, participants reported demographic data, experience with VR, and filled out the Motion Sickness Susceptibility Questionnaire short form. Our population was mostly without experience with VR and presented a mean MMSQ raw score below the general populations. Besides analyzing the full population, we repeated all analysis with two subpopulations. This includes a female subpopulation that previous work has shown is more susceptible to VIMS, and a subpopulation made of the upper 75 percentile of the MSSQ short. For each session, participants fill out an eye group presence questionnaire, a similar sickness questionnaire before and after the session, a visual questionnaire similar to the one applied in Fernandez and Feiner's work. We also included an optional comment field if the participants wanted to report problems with their experience. Finally, head direction data from each session was recorded and decomposed into measures like yaw, roll, pitch, latitude, and longitude. Taking into account the track segments, we also looked at distance, meaning how much they move between readings, and distance to point of interest, meaning the distance between the head direction and the point of interest. The lower the value, the more the participant was looking at the point of interest. In our case, the point of interest was the roller coaster track, and this was based on the dataset saliency maps of this video. Focusing now on the results, analysis was done in R and all data was non-parametric with the exception of spatial presence and experience realism. There was no statistical significant difference between conditions, but the distribution of disorientation, nausea, and oculomotor is consistent with VIMS. The box plot on the left represents SSQ total score before and after the session and the difference between them. Ideally, the latter should be a narrow box plot with the median at 0, meaning that the condition did not cause an increase in symptoms. From our conditions, using only a restricted field of view in blue seems to be the best alternative in reducing VIMS. In terms of presence, the results are expected since using VIMS prevention techniques introduce noticeable visual interferences. Conditions with restricted field of view were shown to have lower scores for general presence and spatial presence, as in a way these techniques are more aggressive and they hide more of the visual periphery. From the visual statements, participants were aware of the visual changes made in each condition, and for brevity we only highlight some of the comments made. Some participants thought that the grid was a mistake, with P10 reporting to be more careful with the blue lines around the visual field. Some participants disliked the rate of change of the field of view. And finally, a participant reported that some of the parts where the field of view got smaller were really strange to experience. My brain kept wanting to focus on the yellow track. So is this behavior exclusive to this condition? Looking at the small example from S2A and S3B, participants use the slow movement of S2 to explore the environment, but during the double helixes of S3B, they are focused on the track. Looking at the head direction axis, there is a similar behavior between conditions, but there is a different overall behavior when we consider the segments. In the blue segments of S2, there is more exploration, either by looking side to side or up and down. When the yellow segment of S3 starts, the more turbulent part of the ride, participants focus on the point of interest, in this case the yellow track. This type of behavior is consistent in other segments, and from the hotspots we can see that there is not a noticeable variation between the conditions. While we cannot compare S2 and S3 statistically, since they have different time windows, we can compare conditions in each of the segments. For the full population, the distance and distance to point of interest are similar among conditions, and no statistical significance was found. However, looking at the female subpopulation, in the absence of an independent visual background, there was more movement in S2 and S3, and participants were less focused on the point of interest in S3. For the upper 75 percentile subpopulation, a main interaction effect was found where adding an independent visual background to a restricted field of view resulted in less movement in S3. Returning to our research questions, optical flow can help to contextualize a video, like for example the small wave pattern in S2B corresponds to equally distanced light poles. And an optical flow can also help identify extreme motion like the double helix in S3V. Conceptually, we can use optical flow in 360 video to mitigate VIMS, but we also need to take into account the media. For example, the existence of singular or multiple points of interest, the existence of a stationary element like the roller coaster wagon that offers consistent low optical flow, and in general, how optical flow is distributed in time and space. Furthermore, understanding user behavior is crucial, since by staying on track, the use of the optical flow as a control mechanism for the techniques was not optimal. The staying on track behavior might have various causes, like participants having prior experience of a roller coaster and knowing the behavior to adopt, or that participants know the direction they are headed since it's a on-rails experience, or that the interplay between the optical flow and the techniques is guiding the participants to focus on the yellow track. Regardless, these two components suggest that roller coasters might not be the perfect case study for VR sickness studies, and further studies could be carried out where ideally the media would have an unknown and variable path of motion with considerable optical flow and a longer duration. Finally, our second research question, how we can apply or combine techniques that mitigate VIMS in VR to 360 video. As expected, using techniques that introduce non-realistic elements are bound to affect presence components. In our case, the more noticeable technique, restricted field of view, affected general presence, spatial presence, and involvement. No statistical significance on similar sickness questionnaire for the full population was found, but the restricted field of view not only produced the lowest similar sickness questionnaire scores, but was well received in terms of comfort, enjoyability, and desire. One of our takeaways is to not only focus on the SSQ components, but to look at the objective measures like distance and distance to point of interest as measures to understand and contextualize behaviors, especially when applied to our subpopulations. In conclusion, with this paper, we presented a two-way repeated measure studies with 24 participants using independent visual background and a restricted field of view, controlled by an optical flow of a 360 video. Using a fusion of quantitative data, knowledge of the media, and the knowledge of the user behavior, we were able to understand if and when these techniques worked, pointing out improvements needed for future studies and for generalization. Thank you, and please check out our paper and supplementary materials for more information on this work.